All right, so what I want to talk about are some of the applications of different phases in terms of an ideal or a pure substance, okay? And so I want to come back to something that we've seen in several lectures, but we're really going to start delving into in the next few lectures, and that is our state or our phase diagram. So if you remember, we could draw a coordinate axis, and on one axis would be one property, one state property, okay? And I've just called the property A and B. Now we're going to specify it, all right? I could put on this axis the specific volume, okay? And then on this axis, I could put the temperature. Now, I could do the pressure on that axis if I wanted. I could do any two, temperature, pressure, or volume. And so why do I choose these? Well, it turns out we are going to do all of them. All right, so we're going to go ahead and do the pressure one at a later time. I'm just choosing to start with this one. So don't worry, it's not that we're excluding the rest, we're going to get to them. All right, so if I have a state, and here's going to be my state, it's a container that has some fluid in it, and this is a liquid, all right? And I'm going to say that my pressure is 1 atmosphere. Now, how can I achieve 1 atmosphere of pressure? Well, let's just say that I have a piston that weighs down this liquid right here, and there's only 1 atmosphere of pressure pushing down on it. So this is a piston, and it's constant pressure, okay? So the pressure is going to be unchanged throughout this. I'm going to show you this system evolving, and the entire time, this is going to be constant pressure. So I'm going to teach you a fancy word, which will come up now and again, and it's the word for constant pressure. So I'll do it down here. Isobaric is the word. So this you can sort of see in this word baric, the word bar, which was our unit of pressure, like it was in the word barometer, okay? So it tells you that we're talking about pressure when we see this word bar, and iso just means the same or unchanging, okay? So constant pressure, our pressure is unchanging, and that's going to be the situation that we study. So here we have a liquid, it's a constant pressure, and let's start it out at, let's see, what did I have? 20 degrees Celsius, all right? So something that is in the range that we're used to dealing with on an everyday basis. Okay, so this liquid could be water if you want to put it in more concrete terms. Okay, so what we're gonna do is plot the state of this liquid on this chart, all right? And because these things are gonna be increasing, I'm gonna start it down here at some specific volume. So remember how I plot points on this chart. I measure the specific volume of this liquid, and I find where on this axis is it, and it's right there. Then I measure the temperature, and it's 20 degrees, and I can mark that right about there. 20 degrees Celsius. And so I can come over and up and plot a point. All right, just like we're used to doing in math on a Cartesian coordinate system, but now this coordinate system is plotting out the temperature versus the pressure. Now, I've got 1 point down. I want to do something to this, and I want to watch that point change. I want to watch and see how it moves. Remember our process paths? We talked about that. If we go from one state to another, we have a process path. Well, let's find that process path, okay? So what I am going to do is apply some heat to this, and that is going to increase the temperature. So remember that the pressure is staying the same, but we're increasing the temperature. Big old arrow to show that this is at a later time. We still have the liquid, we still have our piston, and now this is, let's say we've gotten it all the way up to 100 degrees. Now, it's not over 100 degrees, it's at 100 degrees. That means that we've just reached that boiling point. Nothing has boiled, or we'll use the term vaporized, all right? So nothing has quite yet vaporized. I'm approaching 100 and I'm just arriving there. So if we just stop and freeze our whole experiment and look at this snapshot, we're going to see something interesting is going on. So first on our process path, what was happening as we increased the temperature? Well, we know that the temperature was going up. So we were moving, some component of our process path was going upwards, up with the temperature axis. We also know, because we've talked about the ideal gas law, and just from your intuition, you also know this, the fact that the volume was expanding, all right? And so we know that some component of our process path is along this direction of increasing volume. And so it was some diagonal path like this. We took some general diagonal, okay? And now we're to the point that we are right now, which is at our 100 degrees. Now, what's the name of this phase? It's got a very special name to it. Before, when we're just in liquid, this liquid was only at 20 degrees. It was not just about to vaporize. And so we could call that liquid subcooled, or some people call it compressed, okay? So both mean the same thing, subcooled or compressed liquid. All that big term there is trying to communicate to you is it's not in any danger of vaporization. It's not even close, all right? That's what we had to start. Now we have liquid that's about to vaporize, and the term for that is saturated liquid. Okay? So now we have saturated liquid, and it's almost about to vaporize. Now, let's continue heating it. So further down the line. Now, as this liquid keeps heating just past the 100 point, we know that it's going to start to boil, it's going to start to vaporize, turn into vapor. And so in between, while it's turning into vapor, we're going to have two states. We're going to have some of the liquid, some of the substance that is still liquid, and then we're going to have some of it that is turned into vapor. And that in between, where it's partly vapor and partly liquid, is called a mixed state. So this in-between arrow represents a mixed state. And we're going to keep increasing and keep increasing, and there's going to, as we keep increasing the temperature, there's going to be less and less and less of the liquid and more and more and more of the vapor. Now, that temperature change, this heat that we're adding, is not actually going to increase the temperature. I apologize if I misspoke. We keep adding heat, but where's that heat energy going? Well, that heat energy is going into transitioning that phase. Remember, we talked about the term phase transition, which is where we go from one phase to the other. That's what we're doing, right? We're going from a liquid phase to a vapor phase. That takes energy, and that's something we'll talk about more later when we do a comprehensive look at energy. But that's where that heat energy is going. It's not going to a temperature increase. One way you can see this is to think about the fact that once we have a vapor, in order for that vapor's temperature to increase, it all has to be vapor, right? The system would rather keep boiling off liquid than start heating up the vapor that it has. So any heat that we do in this mixed state is going toward converting that liquid into vapor. It's going into the vaporization process, not to heating it up. So as we look at what our process diagram is doing, the volume is obviously still increasing, but the temperature is not. And so we have a flat line that goes this way, okay? That's supposed to be perfectly straight. Okay, so we're just heading that way until we do reach that magical point where all the liquid has been converted into vapor. And that is the point where we have saturated vapor. So now all of it is in the vapor state, and this is called saturated vapor. Now, remember the saturated liquid was liquid that was just about to become vapor. It was almost there, right on the threshold, right on the verge. Saturated vapor is vapor, because it's all been converted to vapor, but it's just about to go back to liquid. Some of it wants to go back to being liquid, all right? So it's almost about to condense back down into liquid. It's barely vapor. It's like the minimum possible amount of vapor, all right? If it loses any heat, going back down, all right? This is the state of saturated vapor. And this is some point out in here, right? We've been going along, our process has been going along, and we finally reached this point, okay? Some point out in here. Now, if we keep adding heat, our final thing, let's just say we heat this up, and this is still technically at 100 degrees, because we've changed phase, but we haven't added temperature. We keep adding heat, this is just going to get more and more temperature increase and volume increase, right? Because now there's no more phase transition for energy to go into. And this, let's say we heat it up to 300 degrees Celsius, it's just very hot temperature-wise, and it's large volume-wise. And this is superheated vapor. And so that fancy word is telling us that it's just vapor that is not about to condense back down. It's in no danger of condensing back down into liquid. It is really, really, really hot, very high temperature, superheated, and it's not going anywhere. It's just gonna happily be vapor, okay? And so on our state diagram, that corresponds to this. We're increasing again. So we were increasing to start and increasing again. So notice that this flat line sort of interrupts our line going up. It's not just, it doesn't always just increase, temperature and volume go up together. It doesn't always just do that. It's interrupted by this flat line here, which is the mixed state. That's where our phase transition is happening from completely liquid to completely vapor. That's the physical interpretation of this flat line. Now, this line is all happening at constant pressure. Remember, it was isobaric. Pressure's all the same. And so the last thing I want to look at is what happens if we have different pressures. And so on this one, don't take my word for it, but you will have to take the word of the experimentalists who have done this very, very carefully, very controlled, and repeated it many, many times. And this is what our phase change would look like. Let's say that we increase our pressure a little bit. So we're starting at a higher point, say up here. We still go up, we come across, but we come across a little bit of a shorter distance, and then we go up. Keep going, come across. It's getting pretty short now, that distance that we have to travel. See, it's the same shape, but this mixed state phase transition, that's becoming less and less, all right? It takes less and less energy to transition across there. Until finally we have one that comes up and just goes straight to vapor. It has no actual phase transition, okay? There's no mixed state coming across. And then above this, all of them just look like that. They're just smooth lines without this little shelf. So this is pretty intriguing. Remember that each one of these lines is a line of constant pressure. They're different pressures. Here's one, and then here's a little higher, a little higher, a little higher. These are different pressures, but the pressure along the line is the same the whole way through, okay, for each individual line. And so we want to talk about this point right here. That's where something really interesting happens. So what we might do is we might join up all these lines, and maybe I'll use a different color, I'll use blue. So notice that if we join up these vertices, we get something that looks like this. See the shape of that blue line? I've just joined up where the corners of that change. So notice that all of these lines that were flat going across, those were all mixed states. So anything in this region is a mixed state. Right? Any liquid that you would plot on the chart, right? Measure it and put the dot where that state is. Any dot that falls in here is in a mixed. There's a transition going on. All right. Any dot that you would put in here, well, remember this whole region was the liquid. So this would be compressed liquid. And out here, remember any dot out here would be superheated vapor. Okay? And so we have these borders here. And so along one border, we have the saturated liquid line. This means that all of the points here that we could plot that fall along this line correspond to liquids that are saturated. That means, remember, that they're just about to start becoming vapor. And that makes sense. All of our lines, as we traced out the path, once we hit this border and past it, they would start becoming vapor. And then over here on this side, you could probably guess, this is the saturated vapor line. Okay, so these two lines, saturated liquid and saturated vapor. But remember, I said we're going to talk about this point. This is a really interesting point called the critical point. The critical point. And so at the critical point, look what happens. The saturated liquid line and the saturated vapor line meet each other. They become one point. Think about in physics terms. Saturated liquid means that it's just about to become vapor, and saturated vapor means it's just about to become liquid. So what does it mean for them to be the same? Well, anything above this point is a different phase of matter. Okay, it's some crazy liquid vapor state, and our brains, we don't have an intuition for it. Okay, and so this critical point is really interesting. It's not something that we deal with every day because it's at such a high temperature. It's far up on the temperature scale. But once you hit that, if you go above it, you're not a liquid or a vapor. You're some crazy, crazy in-between thing that you have both states of matter coexisting at the same time. And it can be a lot to wrap your head around. But you're going to see this graph plenty of times. And so as we continue to see it, we'll get used to using it, knowing what it is, and sort of how we should think about it. So the next time, what I want to do is this same thing, only I want to do it with pressure, and look at how that enters the equation. Okay? Thank you.